Right, so hi everyone, welcome for this new seminar. So today we have the pleasure to welcome Kajol Paithankar from the Indian Institute of Astrophysics in Bengaluru and the Department of Physics in Pondicherry University. And the topic of the talk will be time delay as a probe of multiple photon spheres. So as usual, there will be time at the end for questions, but feel free to ask also during the talk. And Kajol, thanks a lot for being here and giving the seminar. You have the floor.
So, to thank every one of you for being here, and thanks Professor Kajol for giving me the opportunity to be here and explore the university and research that is going on around here. And today I'll be talking about the time delay, which we can use to understand more about spacetimes, which can have multiple photons here. So let me start by just giving a brief idea about photon spheres. Most of you already know about these things, but let me just do it for completeness. So we all know that black holes bend light around them, and the bending is so strong that beyond certain point, all the light rays will fall inside the black hole and will form the central dark patch in the black hole images. So the limiting curve, where the light just goes around the black hole in circular rays, is something called photon sphere radius, and on that sphere, light just goes around in circles. So that particular radius is what separates the rays that falls inside the black hole and the rays that goes around the black hole, bend around, say 1 time, 2 times, so make n number of loops, and then come out and we can observe that. So this critical curve is what defines the angular size of the central dark patch in the image of the black hole. And we call it black hole shadow. So this alpha is angular size. We can similarly say there's some radial distance on the observer's side. Okay. So this creates an image like this, and this is what I will call a photon ring in the black hole image from here on. This is just a background, and in this background, if we try to understand how it reflects in the equation, we first have to write the equations of motion for photon, and in that equation we have a kinetic part, a potential part, and some constant, which is the total energy for that motion, and the potential looks something like this. So here you can easily see that depending on this B is the critical, because B is the impact parameter for the photon, which is constant for each photon, depending on its energy and its angular momentum in that space. So depending on this B, if the photon has impact parameter less than the critical value, there is no barrier for it to stop, and it will just fall directly inside the black hole horizon. If it is greater than that of critical value, then it will experience a barrier, it will turn back at this point, and it will go back to an observer at infinity or far away from the black hole. So this critical value is what separates these two kind of trajectories. And the ring that you saw in this earlier slide is what corresponds to close to all the trajectories which are close to this critical impact parameter. Okay. So once I have this potential structure, I know where the horizon lies, I know where the peak is. This will give me the radius of photons here. The magnitude of peak is what will give me the critical value of critical impact parameter. This just comes from the equations of motion for photon. And once I have this photon sphere radius and the value of critical impact parameter, it's easy to find what is going to be the angular size of the black hole shadow at the observer's location. So this factor is same for observer. Once you fix the observer's location, and only the critical impact parameter is what defines the black hole shadow depending on what space time you are in. Okay. So this is what we see in Schwarzschild spacetimes or any spacetime which has a single peak in potential, and in usual vacuum spacetime this is the case in general relativity. Okay. Now there are some solutions recently in the literature, and many of them can exhibit multiple photon spheres. So some cases is where people have considered some perturbation to Schwarzschild black hole. Then we know that there are some reflections to the Schwarzschild black hole, and how to parameterize this is what is done by this JP and RC metrics. So they define instead of just 1 minus 2m by r, now there are higher orders of 1 by r in the metric. This can lead to multiple black photon spheres. Other case is hairy black hole solutions. So there are solutions for resonance of some charged black holes and charged black holes. This also show multiple black holes, multiple photon spheres in some parameter ranges. There are black holes in nonlinear electrodynamics, and all these black holes have been explored for their energy conditions, so strong, weak, null energy condition, and dominant energy condition. And it turns out that except strong energy condition, the rest of the energy conditions are not violated, and so the black holes are not black holes are physically viable, so we can consider them relevant to study or in physical scenarios. So once we know that there are solutions like this in the literature, the next question to ask is what information we can uh, get from them or probe them in what different kinds of ways. So through the observations. So one way is through black hole shadows, where we know once we have two multiple photons here, we can see instead of one ring, we are expected to see two rings corresponding to the two peaks in the potential. Additional thing is something which I'll be talking about today, which is quite time delaying for such multiple things. So I'll start with setting up the space-time. So say if my space-time has this kind of metric, and I choose this kind of metric function where I, instead of just 1 minus 2 by r, now I have higher orders of 1 by r1, 1 by r2. I have kept it this simple in the simple form because once I have this form, my rest of the calculation simplifies. So say for horizon, I know this f of r equal to 0 will just give me a cubic equation. And for cubic equation, I know how to write the roots of the cubic polynomial. So the roots simplify in this way, and then I can just figure out which one is the largest and which one is the smallest root. So when all the three roots are positive and real, so they make physical sense, they follow this kind of inequality. So event horizon is defined by the largest root, so here it's RH1. And in some parameter space, when two of them are complex conjugates and only one solution is real and positive, that is the solution that defines my horizon. So similar way, now once I set up this diagram, now I can study what happens to the photons in this diagram. So the equation that governs the photon motion is given by this. So this is the kinetic part, this is the potential part, and this is the constant on the right hand side. And this B is the impact parameter, and the potential is given by the metric function f of r divided by r square. This is the usual case which is in given release of Schwarzschild. This is same thing follows. So once I have this, now I can find where the photon sphere area are just by setting the potential derivative of potential to 0. Again, this is a quadratic polynomial, and then I can figure out the roots of this polynomial in simple form, closed form. I can write those now, and everything is just function of norm ABC, the parameters that are defined in the metric. Again, when all these three roots are positive, I can find the inequality. Which one is the smallest and which one is the largest. So I know now for sure that there are three photon spheres in the space-time outside the horizon, and they are spaced at, so R1 defines the innermost, R3 defines the outermost. So I know their locations where they are with respect to each other. Okay. Once I have this setup in the background, then I can even figure out which of these photon spheres will be stable and which of them are unstable, just by finding the second derivative of potential. And it simplifies in this nice format where I can write everything in terms of just the three roots that I have to start with. And I know now R1 is the smallest, R2 and R3 is the largest. So this subtraction, I know which gives the plus sign, which gives the minus sign. And then I can simply say that the second derivative is negative, this is negative, and at R2 it is positive. So just based on the equations, now I can have the whole structure of how the potential will look like. That at R1 it is maximum, at R3 it is maximum, and in between at R2 I will have a minimum of the potential. The magnitude is something that I haven't still commented about, but at least we have how the potential will look like starting from horizon to say infinity. So once I fix some values for say ABC parameters, then I can find that the horizon is then R1, R2, R3, all the three photon spheres, and what is the magnitude of potential at each of those points. So So I have chosen the value such that my potential at first peak and potential at second peak, they have exactly same magnitudes. And the potential well in between, that we call the potential, the depth of this changes with for different parameter spaces. So now since we know that the size of the black hole shadow, so the central dark patch, the boundary of that, is defined by the magnitude of peak, not by where the photon sphere is, not the value of R1, R2, and R3, but by the potential at R1 and potential at R3. These two black holes will form exactly same size of the images at the observer's location. So if the observer observes the shadow, the ring sizes will be same. Okay. So then for black holes in multiple photosphere, we'll have degeneracy just by the observation of black hole photon rays at the observer's location. So then what is the solution to this? Is there any other observation that we can do and resolve the degeneracy? Is what we try to address in this paper. So we define some quantities which we can then work around with. One is the angular distance covered by photon. So when photon goes bend around the black hole and make one loop, two loop, three loop, I can figure out what is the total angular distance covered by it. And this is just a simple expression. Same way we can figure out what is the time taken by that photon. And then this is the turning point, which is simply defined by where my r dot the kinetic part is 0. And then I can figure out what is the turning point for that particular. Additionally to these three things, I can define what is the total number of half orbits. So when I know delta phi, the total angular distance covered by photon, I can just divide it by pi, and whatever the closest integer that I get, the smaller integer that I get close to it, is what will define my complete half orbit. So if it takes 1 pi, 2 pi, or 3 pi, or 4 pi, the number of loops that is the photon is making around the black hole. Then additionally, I have divided this total n in terms of two parts, so n and now. I will explain this in a minute because this helps me categorize the orbits, and other than that, it doesn't have any qualitative features as such. So this is how the photon trajectories will look like if I consider all impact parameters around the black. So this dashed black line, hope you can see it. This is the outer photon sphere at R peak that we saw in the image. So the outer peak in the potential. This black dashed line is the inner photon sphere, and this is the first peak that we saw in the potential image. So these are the trajectories which are all outside the outer photon sphere, and this is how the trajectories look even in Schwarzschild space. So once I go on decreasing the impact parameters, once I make the trajectory comes closer and closer to the black hole, it will make more number of turns around the black hole. And this is what I mean. So when I find that delta phi, how many closed loop it makes and goes back to infinity. So the green trajectories have this delta phi less than 2 pi, so I've just separated into parts for now for understanding. And the red lines make more number of loops because their impact parameter is closer to the critical value and they bend very close to the photon sphere. Now there is another kind of trajectories in this case because now we have two photon spheres that fall inside this outer dashed black line, outer photon sphere. And here you can see that once you decrease the impact parameter or as the trajectory gets closer and closer to the black hole, it makes more number of turns. That is a monotonic relation. The closer the trajectory, the more the angular distance covered. Here that's not the case. So even here if you can see there is a very small red part where there are n number of trajectories, and as I make the impact parameter closer and closer to the black hole, the trajectories start first they make more angular reflection, and then they again start making lesser angular reflection at some point. So this will be clear in a bit when I show you individual trajectories instead of all trajectories altogether. So this is a comparison of these kind of multiple photons where space-time is short-shaped. So in short-shaped, we just have this monotonic relative. Once I decrease the impact parameter, my angular distance goes on increasing. So the photon gets more number of photons. But when we have multiple photon spheres, this part outside the outer photon sphere is qualitatively same. But inside, the more angular distance is covered closer to these critical values rather than in between them. So the angular distance decreases up to a certain point and then again increases close to the inner photon. So it's like saying photon makes say 9 pi, 8 pi, 7 pi orbits close to here, then they make 6 pi somewhere around here, and then again it increases close to the inner photon. So it's not the monotonic relation that we had here. In fact, it has a minimum somewhere in here. Same thing happens with time. When I calculate the time, it increases close to the peak because it's making more and more number of loops exactly close to the critical value. And in between, there is a minimum of time. So if just vaguely, if I draw a line, say at 300, you can see that I will see multiple images, so 3 simultaneous images at one time. So this is not what happens in case of structured space-time. At one time, we'll just see one image formed by corresponding to one delta, so one number of images. Here we will see 3 images. So this will be clear in a minute. Other thing is there is a minimum value. So I can find out what that minimum value is. And the minimum value here and minimum value here of B, the impact parameter, is same in both the cases. And I can figure out what this is. So if we make observations correctly beyond certain minimum time, say T minimum here, then we'll definitely see multiple images at the same time. Made by caused by multiple photons. Okay. So these are some of the images. So if I fix my source and fix my observer around such kind of black holes, then I can figure out what trajectories will connect them starting from source to observer. And these are the trajectories which corresponds to say number of turns n equal to 6. So this is the trajectory which just loops outside the outer black dash line, which is outer photosphere. This is the trajectory which falls directly inside. So since you can see my observer is here, it starts from here and it doesn't even make 1 pi orbit around the black hole before falling inside the outer photosphere. And then it makes all the loops close to the inner dash line, which is inner photosphere. Then there are third kind of trajectory, which makes at least this first pi orbit. So this light line, if you can see, this is my light line. So this first pi orbit is made outside the outer dash line, which is outer photosphere, and then rest of the loops are made inside. So this is what I this is how I divided the total number n in 2 parts. How much it covers outside the outer dash line and inside the outer dash line. So here it's the total n equal to 6, all of them covered outside. Here all n equal to 6 covered inside, and here 1 is covered outside and the rest of them are covered inside. So that's how I divided it, just to categorize them in 3 different ways. So I'll call them just green, red and blue trajectories from here onwards. So simple. Okay. The same way, once we define fix the observer and source, we can find the even order, odd ordered images. And here you saw the even ordered images will appear somewhere here. If I just extend it backwards, the odd ordered images will appear somewhere over here. If I extend it back, so they will appear on the opposite side of the black hole. If I just draw a straight line through the black hole. Okay. So this is again finding the angular distance and time, and these are the red dots, the dots that are trajectories that connect the source and observer that I showed you sometime back. If I fix the observer, but I keep the source on the whole ring of that same radius, this is the curve that I will get. So to get images from source which is spread around the black hole, I have to consider to get a continuous curve, I have to consider source to be spread all around the black hole, not at just some point with respect to the observer. Uh, so even here you can see that if I choose an appropriate time, so around 300, we will be able to see this 1, 2, and 3 images in this some time interval. Same thing will happen here. But now, in case of black hole 1, which has deeper potential well, and black hole 2, which has shallow potential well, in the shallow case, we'll find the images corresponding to 6, 7, 8, and 9. We'll see them sooner than in the case of deeper potential. So this is one thing that we can figure out, how earlier we see the images, that will tell us whether our potential well is shallow or deeper, just qualitatively. And then we have to maybe fit some space time to figure out what exactly the space time is. Once we have that, we figured out all the trajectories that we can till some higher order. And this is just animation to show how they will appear. So the images will start from n equal to 2, and the even ordered images will appear here, odd ordered will appear here. So it will start from 2 here, then 3 here, 4 and 5. Then from 6 onwards, we will see 3 images. One flows to this outer photon here, then one flows to the inner photon here, and then one somewhere in between. So let me just start it. So this is image corresponds to n equal to 2, this is n equal to 3, then n equal to 4 will appear here, and 5 will appear here. And this there is a difference of time, which larger difference compared to the same order images. So when n equal to 6 images appear here, the 3 images, they appear in a very short interval of time. So this is 6, 1, 6, 2, and 6, 3. The same thing is 7, 1, 7, 2, and 7. Then again the 8th, n equal to 8th order images will appear here, and 9th order images will appear here. But the duration of time between the two orders is much more than those of 3 images of the same order. So if we choose an appropriate time, then we'll be able to see 3 images. Okay. Then once we have this multiple images, we try to see how, based on the category, is there any sequence of in time that we can figure out. So it turns out that the 3 images that I showed you earlier, blue, red, and green, they appear in a specific order. So the green image will always appear first. So once I pick the order and say this, the first image will always appear close to the outer photosphere. These are the green ones. Then the second image will appear close to the inner photosphere. These are the blue ones, and the third will then appear in between, which is not what happens in case of Schwarzschild. In case of Schwarzschild, the images appear later as they move closer and closer to the black hole. Here, first image which is outside, second appears inside, and the in between image is what appears at the later. The same thing happens for black hole too in initial cases, but then beyond certain point, even this sequence changes. So this is even difficult to understand, because this is like saying the first image will appear at the innermost point close to the black hole, then second will appear at the outer photosphere, and then the third one will appear here. So the sequence is very much juggled up, maybe I say. So this is still something that we are trying to understand, why the sequence changes and why it is in this particular. Okay. Then we thought of doing it for some compact object, because if you see the potential here, it's not just the depth of the potential well is different, but in fact even the location of photon sphere is different here. So if you just see values of R1, R2, and R3, they are different. So you can see the turning points. If I draw a horizontal line here, it's not just that it's experiencing different potential, right? But even the turning point is much larger for black hole 2 compared to black hole 1. So we want to understand whether this is the qualitative feature of potential well depth only or even the change in the terminal gap. So we tried to do it for some compact object. I'm just calling it compact object because it doesn't have a horizon to start with. So we were more interested in potential structure rather than what object it is. So we just have some 6 parameters because this allows me to fix the value of 3 photon spheres. So I can make them exactly same as that of one of the black hole. And then I can fix the magnitude of potential and I can make it same as black hole 1. And the only change compared to black hole 1 here is the depth of the potential then. All the 3 values of photon sphere radius are same and even the magnitude of potential is same. So the only difference that will get compared to black hole 1 is from the effect will be from the depth of the potential well and not from any other scenario. So if we do this and then do the same analysis starting what we did for the 2 black holes, we still figure out that there is a change in when the images will appear, the 3 categories that I showed you earlier. And if you see here, there is a very small difference. But for black hole, for which the depth is smaller, shallower, the images will appear first. And for compact object, for which the depth is more, the images will appear later. So this we think is a definite qualitative feature that the shallower potential will make the images appear earlier rather than the deeper potential.
Yes, did you try to get an analytic expression for the dependence of the time delay on the depth?
No, because the equations are so complicated that you can't solve them analytically. But I try to plot how the time evolves, and this change in time is accumulated over the entire trajectory from outer photosphere to inner photosphere and then back. So it's in case of Schwarzschild, we can approximate it close to the peak and then figure out because the majority of time is spent close to the photon sphere. And the rest of the trajectory is approximately same for all the orders. If not the if I don't consider the first and second direct and first order. But here that's not the case, so I can't say that the time is accumulated over just this small region or just close to the peak. It's accumulated over the entire trajectory between the 2 photon spheres. So that made it difficult.
Right, but looking at the integral, you couldn't try to have an argument that if it's deeper, then the integral gives you a larger. It's difficult, I understand, but maybe not actually get an expression for the time, but try to get a sort of order if how it depends on the depth of the potential.
So we thought about it. The issue is this potential. Here it's a potential. Right? So the difference when my depth is more, this difference is more, and this is in denominator. So I have a larger value denominator. But if I just multiply and divide by r square here, then my f of r by r square will be potential. And then I have another potential, which actually has a, because it's deeper, its actual value is lesser than the other one. And so I have a smaller quantity here. So I have a smaller quantity denominator and a larger quantity in denominator. And some combination of them is ultimately giving me this time value. So it's not that straightforward to try to understand it, but we couldn't figure it out at least.
But perhaps you could try to cook up a V of r where this integral would be exact, not exactly the ones that you've been using from those metrics.
Okay.
And with one parameter that would change the depth of the potential. Well, I didn't try.
Sorry, as a follow-up kind of, but the V, you say it was f over r squared, no?
V is f over r squared.
So I don't know if it's possible then to compare kind of this, because f would be also in the square root. I don't know if there's some expansion that could be done or something, so that
So I
you
can
could
write
see the
everything in
compensation.
terms of just R and D,
Yeah.
but
The question is if you could cook it such that this would be an exact integral. And maybe with one parameter so that you could just choose it.
so the
But maybe it's a dream.
examples that I talked about, they majority of them have three
I
parameters.
understand.
And once I have three parameters, it's very difficult to find the potential which will only differ in depth with just three parameters. So that's why I chose those six parameters so I can fix everything else and just keep that one difference in the total. Otherwise, it was very difficult. So these are the conclusions that if we choose the proper time frame, then we will be able to see multiple images in the same time interval. Then that should be sufficient for observation of multiple images. And we have to consider the source to be a flash of light and not the continuous source because then it will be difficult to observe. The other thing is, when I study two black holes, the shallower potential, in this case of shallower potential, then the images appear earlier. So based on how earlier the images appear, we can say whether how the potential varies in between the two peaks, even though the photon ring size are exactly same in two cases. Then there are these images which appear between the two photon rings, and they will always appear at the last, irrespective of whether I'm studying the black holes or the compact objects. And this is something that we are still trying to understand why it happens, because in just the simple terms, if I try to understand, the closer the photon is going to the black hole, the larger distance is covering, and so it is supposed to take longer time, which happens in case of Schwarzschild. But here, it's the other way of the image appear closer to the black hole first and then outside somewhere. So it could be because of the potential well, but exactly why it happens is what we are not clear about. And then here with compact objects, we try to isolate the effect of potential depth and keep everything else same. And it still turns out that in case of shallow potential well, the images appear early. So these are conclusions from this paper, and this is still on our side. So I hope it gets published. And these are other publications that I have. So I'll just tell you briefly what they're about. The first two papers are on accelerated trajectories around black holes. So we know that when we have in case of flat space-time, in Minkowski space, if we have an accelerated observer, even it will see the vacuum as made of fringe particles. So it's called an Unruh effect. So we were trying to see if there's a similar effect in case of black hole space-time. And we do found the trajectories, but again the equations were so complicated that we couldn't do the Unruh effect calculation, so we left it there. But we have the solutions for uniformly accelerated trajectories, which are not on a fixed path, so they are not stationary. They actually move. They are radial trajectories. They move in the radial distance. So because we have these kind of trajectories, we can actually see how the vacuum is different for each of these trajectories. But this is just a hope that we'll see someday. The third paper is about Selby-Monroe effect in case of Brent-Starling radiation. So we know that accelerated charge in vacuum emits radiation, and inertial observer will see that the accelerated charge is emitting radiation. But if we have accelerated observer which is accelerating with the charge, then what kind of radiation it will see? That was the question. And for the two observers to agree, the inertial one and the accelerated one, we have to consider the background to be made of regular particles and not vacuum. So for inertial observer, the background is vacuum. For accelerated observer, the background is made of regular particles. When we do consider that, then only the two observers can agree and say the transition time of the transition rates of particles are matching. Okay. The third thing is about some bounds that we found on this regular trajectories. So what happens is if we increase the acceleration beyond certain value of acceleration, the trajectory doesn't turn back at some radius and doesn't come out to infinity. It just falls inside the black hole. So the way we had photons here, in case of like trajectories, photon trajectories, there is this bound on accelerated trajectories, which are actually massive particles. So we found that there is this relation between these bound on accelerated trajectories and photon sphere. So in case of Schwarzschild black hole or any spherical symmetric black hole, which has Schwarzschild kind of form, so my GTT metric function and GRR metric function are just inverse of each other. If I have that symmetry, then it follows that my photon sphere radius is what defines the turning point, the closest such a trajectory can go to the black hole. And the magnitude, the critical impact parameter value, is what defines the magnitude of acceleration in case of accelerated trajectories. So these bounds are related to the shadow in this particular case. So this paper was about that, and this final paper was published last year. It was about studying photon region. So in the way we have photon sphere in case of spherically symmetric black hole, in case of rotating black hole, we have photon region, where now in that region we have trajectories which are unstable, and they are the limiting trajectories. So the photons that fall inside will be lost to the black hole, and they will form the central dark region in the black hole image, and the ones that emit escape to outside will form the image of black hole. So for such photon regions, we know how to find those regions in case of kind of black hole, where we know that the equation simply separate. So I can write separate equations for T r theta phi in case of separate the solutions. But if they don't separate, then can we even comment on what the photon region will be, where it will be? Will it be there to start with? So this is our exploration of that. So these are my publications, and the one that I presented now, it is still under process.
Thanks a lot for the very nice presentation. So we have now time for questions.
Kajol, thank you very much for your talk. I don't understand one point. Can you come back to the slide where you say in the middle about simultaneous, that you will see three images simultaneously? Yeah, so here. So when you say simultaneously, you actually mean that they in principle will exist after some order, or you really mean that they will have the same time delay, all three images?
So this is a continuous curve. So when considering the photon is coming with all impact parameters, this won't happen if I have a flash of light. So, and a fixed observer and fixed sources, not all rays will reach to the observer.
Yeah. So how I understand these pictures? So if I fix observer position and source position, I look at the left picture, and then my delta phi will be fixed. So I plot the horizontal line, and I got three images. And for these three images, I got I got three specific impact parameter, three variables. And now I look at the right figure and see which T observable will be for these three impact parameters, which I already know. And it would be very great coincidence if this T for all these three different impact parameters will be the same. So they will exist, but they will probably not have the same time delay. So what do you mean simultaneously in this sense?
So if I fix a source and observer, they are not exactly same, then we have to see at this kind of way. So say, okay, this is time, right? So if I see this, say first dots.
Yeah.
So this one, and this one, they are in some specific time interval. So we should be able to see them one after the other.
Okay, so they are not simultaneously. So it's a bit confusing to say simultaneously.
This is simultaneously when, if I just consider a whole ring of sources. So starting from observer, I can send ray with all impact parameters, and they will reach to some point in source.
Well, yeah, it's maybe not very good word in this sense. When you say about time and simultaneously, it's
if I have a
really
ring
like
of source, then I will see simultaneously.
Maybe three images can coexist would, address this concern.
So not simultaneously, but we can see maybe in short
Yes,
time.
yes, that's clear. Yeah, that's clear. Yes, they will exist. Yeah, that's okay. Yes, thank you. Thank you. Very interesting. Yeah.
But actually, as a sort of follow to that, but what if, like, if you put like units, what would be the actual time difference, say, because
Who knows?
because maybe it would be instantaneous for intents and purposes, or say, okay, not exactly the same question, but how does it compare? So when you showed like this animation, we get a sense of it, but would be the scale or the order of magnitude of the time between these simultaneous images and the time between two different number of tones? Is it like 10 times faster when it's the same order?
I haven't calculated the orders, so I can comment on that. But I hope that depending on black hole's mass. But the thing is, here I have chosen some ABC values. Those are black hole's parameters, so that's what defines a black hole. So depending on what they are, I will have different potential, and then everything changes. So till now we just know mass of two black holes, so I don't know how to fix the rest of the parameters and then comment on that.
I guess the generic point is, can you make the difference between the simultaneous ones and the not simultaneous one? Even it requires to have one source giving a flash rate, which is already.
I guess related to that is how rotation will also impact on these triplet of images.
I don't know whether, but is there a solution where we have such multiple photon regions in rotating black holes?
In some paired black holes, they have these ones with synchronized air. In some regions of the parameter space, as you mentioned, in the case of the Ryzen-Nordstrom with the scalar hair, but that's very coincidental. But there's other models with rotating black holes, and you have these multiple
Photon regions.
yes.
Go to the lateral plane. Go to the lateral plane.
That's always
Everything will be circular.
And of course, you will not have interoperability in some of these cases. So that's, as you mentioned in your last paper about studying these photon regions, it's much more complicated.
But here even I integrated that numerically, so
Sure.
if it's ultimately numerical integration, then it should be good.
It should be good.
More questions? But there's no one online, so I mean, you can still ask questions during lunch and during the next few days. So Kajol is with us until tomorrow, so you have more opportunities. And thank you again for the talk. So just